Thank you. So thanks for inviting me. Feel very free to interrupt me. I might not see if you do a hand up thing, so please just don't be embarrassed and just interrupt me verbally, and that's totally fine. So I'm going to talk about a couple of papers. These two, I think, especially the second. I'm going to start with the second one, and that may be all we do. These papers are with Shubham Chowdhury and Aditya Hebar, who are postdocs at ICTP in Italy, and Ruby Kondakar, she's now a graduate student at Oxford, but she was an undergraduate at Cambridge when she worked on this project. So let's see. So I understand bootstrap as a sort of concept, which is to approach physical systems not by trying to solve a particular model, but considering some class of models and understanding what the sort of constraints are that follow from very basic physical principles on this class of models, right? So the most famous bootstrap, I guess, is the CFT bootstrap. CFTs are very super constrained, right? So you can really, the constraints completely specify them to a discrete set. But there's also the closest to what we're going to do, the direct inspiration for what I'm talking about today was the S matrix bootstrap. So I'll say a couple words about that and just as inspiration. And now an S matrix is not as constrained as a CFT, right? So you need to put some more information in, right? And so the philosophy might be, you know something about the UV of the theory. The S matrix has some bounds and some analyticity properties. And with the UV plus the analyticity plus the bounds, you try to say something about the IR, right? That's the spirit of because a holomorph, analytic objects are quite constrained, and so that's the approach. So indeed, so in the S matrix, maybe there's some kind of scattering process, and then you have, let's say maybe it's a 2-to-2 scattering. You expand the S matrix in partial waves, right? So there's some sort of amplitude for the process. Maybe it depends on the angular momentum and on this S variable, which is sort of the center of mass energy, roughly. And then these partial waves have some analyticity and positivity properties, right? So this is going to be analytic in S over some domain. And it also has some boundedness properties. So for example, for real S, of course, when you say analytic in S, we're thinking about complex S. And for real S, well, in fact, the unitarity implies, among other things, the imaginary part of these amplitudes are positive, and in fact, they're bounded by 2. In fact, you can write down stronger constraints than this, but that's an example of the kind of thing you can say. And so then, as I was saying a minute ago, the idea perhaps you want to say something about large S, you know something about the UV, you've got these properties, and you try to constrain the small s behavior, for example. Okay. So this is the general kind of philosophy I want to implement, but instead of S matrices, I'm interested in condensed matter systems today. And so the idea is to apply this to lattice models, but really quantum lattice models, okay? Not just statistical physics, so with an energy, okay? So lattice models in condensed matter physics, for example. I'll give you some examples in a minute. Now, lattice models don't have an S matrix, but what a very natural object to consider is the retarded Green's function of some operator, okay? And so the retard, in fact, I'll write it down later exactly what it is, but there's given some operator O, it has a retarded Green's function, could be at finite temperature, zero temperature, that doesn't matter. It depends on frequency and momentum. And this object also has some well-known, and I'll review them, positivity and analyticity properties. But the ones that you probably know very well, for example, there has to be analytic in the upper half plane, and that the imaginary part has to be positive on the real axis, okay? That's not quite enough. That's not as strong. Here we have, for example, an upper bound as well as a lower bound, right? And this upper bound really comes from unitarity. And the analyticity that you get from a light cone is stronger than just causality of, causes coming before effects, right? There's a stronger causality. And so to be able to implement this kind of bootstrap program, we need stronger notions of positivity and analyticity for these retarded Green's functions. Okay. So what I'm going to tell you about is how using something called Lieb-Robinson causality, which I'll review for you in a second, or I'll just tell you about, is going to let us prove stronger analyticity and positivity properties for these objects when they exist in a local lattice model, which I'll define for you in a second. Okay, so I want to establish, and then we're going to use those to constrain things like diffusion or certain kind of non-Fermi liquids that I'll describe. Yeah, in the IR, right? So this Lieb-Robinson causality is a UV constraint, okay, that comes from really the interactions on this lattice, and we want to say something about the IR using these properties. Yeah. Okay, so let me tell you about Lieb-Robinson causality. So obviously light cones are, an absolutely fundamental fact about relativistic physics. But perhaps remarkably, although as we'll see, not too surprisingly, there is also a light cone in lattice models. Okay. Now, this light cone is not as strong as the relativistic light cone. It's a little bit leaky. It has exponential tails outside the light cone, as I'll review to you. And so what the first result is going to be is that even though in real space and time, the light cone is not as sharp, right? In a relativistic light cone, the commutators just vanish outside the light cone, right? There's a step function. And in this Lieb-Robinson light cone is not as strong as that, but nonetheless, its Fourier transform in frequency space, so how it constrains the omega and k dependence, it's almost as good as a relativistic light cone. Okay, and so that's the first point I want to make, and I found, yeah, I think it's quite interesting. So what's the setup, right? So the setup is there's some lattice, so you have a series of points. It doesn't have to be a line, right? It could be 2D, 3D, 10D, could be a triangle, could be a square lattice, whatever you want, okay? And so there's what does lattice come with? So it comes with some spacing A. So there's a distance scale. Of course, for more complicated lattices, there could be multiple distance scales. It's just details. And then there's a Hamiltonian on this lattice, and that Hamiltonian comes with some energy scale. Okay, so let's imagine for simplicity, so a local Hamiltonian would typically mean that the Hamiltonian is a sum of terms that are supported on a finite number of lattice sites. The simplest case would be just a nearest neighbor hopping, right? There's some Hamiltonian that connects nearest sites. Okay, it doesn't matter whether it's 2, 3, or 4. For the simplicity, let me just imagine its nearest neighbor, right? So for example, the full Hamiltonian could be something like the Hubbard model, right? So what would that be? That means you'd have an electron that could hop from one site to another one with some energy T, and then there could be some on-site term U, which is something like sum over the sites, the density on that site squared, something a bit like this. I'm being a bit lax. I haven't written down the spin indices and so on, but roughly this term would allows electrons to hop from one site to another one, and this one penalizes you for having two electrons on the same site. It's like a Coulomb. It's like it represents a Coulomb repulsion, right? The electrons don't want to be too close. Doesn't matter. It's a typical. I'm just showing you this is an example of a nearest neighbor Hamiltonian, and so I would write this as a sum over I of H of I, right? The Hamiltonian coupling a pair of points. That's a local model. So this model is an example. So models of this form are local, right? They only couple finite number of points, but it's also bounded in a very strong sense that the operator norm of this H is some finite thing, right? Because these are fermions, they can be up or down. There's basically four on any given, if it's a spin half fermion, there are only four possible states on each side, right? Unoccupied, spin up, spin down, or one up and one down, right? And so it's a finite dimensional. These HIs is basically a 16 by 16 matrix, right? Because there's four states on each site, and so there's 16 total states, and so the matrix, the Hamiltonian acts on the space of these two sites in general. And so it's just a 16 by 16 matrix with finite entries, and it's bound. So it has a finite norm and it's bounded. Okay. So this is the arena that we want to work in. So there's two scales. There's the lattice spacing A, and then there's this norm. There's an energy scale, the UV energy scale given by given by that, right? So this is a lattice model, but at long wavelengths, this could, well, typically, if it's not gapped, it will flow to some kind of quantum field theory, right? And so I want to understand what constraints this lattice locality and boundedness imposes on your IR quantum field theory. Okay. So now these are the ingredients we need. So just to be clear, it's sort of clear with a distance and an energy. You can define a velocity, right? Which is a times, I'm going to call this little h. Okay, that's just a microscopic energy scale. Okay, and this is going to be the Lieb-Robinson velocity. And so to give you an intuition for it, so again, we have this lattice. So suppose you start with some operator that's localized on some site on the lattice, right? So for example, maybe that we want the C dagger operator on site 20, right? This is the 20th site on the lattice. Okay, it's there. Now we want to if we want to time evolve this operator in the Schrodinger picture, sorry, Heisenberg picture, what do? Well, you commute it with the Hamiltonian, right? And so as time passes in one time step, just imagine for a moment time is discrete, you commute it with the Hamiltonian. But if the Hamiltonian only involves the nearest neighbors, this can only involve some operator at the site 19, some other operator at the site 20, and some other operator at the site 21, right? Because the Hamiltonian only couples this site with the two neighboring ones. Yeah. And so this operator, after one commutator, gives you an operator that exists on these sites. You commute again, you get some operator that exists on these sites, and roughly this is the light cone. Yeah. So the spread of the operator with time is sort of linear in time because every time you commute, the operator can grow. This is a little bit too naive, this picture, because time is continuous, it's not discrete. But well, that's the idea, right? And this velocity, the rate every commutator at most gives you an h, and the amount it grows in each step is a lattice spacing, right? And so the natural velocity associated with this light cone is of this order. Okay, so this is the Lieb-Robinson light cone. So now let me give you the theorem that Lieb-Robinson proved, but this is the picture behind it. So it's really strong. Okay, so this is UV stuff. So it's all about operator norms to begin with. So if I've got something like this creation operator C dagger, again, these could be spins. They don't have to be fermions. It's just what I'm having to do. At some site alpha on the lattice at time t, and to commute it with some fermion at site 0 on the lattice at time 0, right? That's sort of a correlation, right? And we'll look at the operator norms. The operator norm is the biggest eigenvalue of the operator, right? It's the biggest this operator could be on any state. It's the biggest. Consider the expectation value of this operator on all possible states. The biggest it could be is this operator norm. And so let's call this quantity C of the lattice point. So x alpha is the coordinate on the lattice and t. So this is an operator norm. This bounds the Green's function because this is the biggest it could be. So the Green's function, which would be the same commutator, I'll be a bit schematic, but now in the expectation value in any state, for example, the thermal state, if you wanted to, which would means thermal state means the trace against the e to the minus h density matrix. Okay, this doesn't have to be positive, so the absolute value of that is certainly less than this operator norm. Okay, so because this is the biggest it could be in any state, and so it's bigger than it is in a particular state. So this sort of very microscopic object upper bounds the correlation function in any state. Okay. Now the Lieb-Robinson bound is an upper bound on this guy, so that in turn upper bounds any state. And so Lieb-Robinson, it can be stated in various ways, but one way is the following. So C of t and x alpha is less than, okay, let me just write it down, k e to the h t x over a. You know what, sorry, I can do better than that actually. Let me do it. Vt over x over a, and this is for x bigger than Vt, and it's 2 for x less than Vt, where V is some constant times A H, where H was the norm of the Hamiltonian. This is the velocity I wrote before. There's some order 1 constant that depends on the geometry of the lattice. Okay, not important. Okay, so but what does this say? So this is an operator norm. The norm of C itself is actually just 1. If they're spinless, let's say spinless fermions to keep it easier. So okay, it's a simple operator. Okay, it's just a 2 by 2 matrix, like 0, 1, 0, 0, right? And so it has norm 1. And then when you take the anti-commutator, you add them, and so you get a 2. It doesn't matter, right? So the norm of this operator can never grow bigger than 2 because there's just not enough stuff. The Hilbert space isn't big enough. Okay, that's not very interesting. This is inside the light cone. Yeah, but outside the light cone, you can have the k is also just again an order 1 number. You get this. So because we're outside the light cone, this quantity here is less than 1, right? In this regime. And as x is much bigger than the lattice spacing, this gets big, right? So a number less than 1 to a big power is exponentially small. Okay, and so this is saying there's an exponential suppression outside the light cone, outside the Lieb-Robinson light cone. Yeah. So this is what Lieb and Robinson proved. It's not quite phrased like this in the original paper, but this is what it is. Yeah. So pretty cool. Okay. So it's a very microscopic light cone. Okay. This velocity is defined at the UV, but there you go. It's a light cone. And so yeah. Any questions about that? Yes, it needs to be. So you might start running into problems if your interactions decay with power laws in distance, but yeah, as long as they're sufficiently local, you always get this. And all the geometry of the lattice, it just goes into the various numerical prefactors. Yeah, that's right. Yes, yeah, as long as it's finite, it's fine. Yeah, and even yeah. That doesn't matter. Yeah, yes. So like I said, so the even it could be all as long as it decayed exponentially, it could even be an infinite number of points. So the but like something that again like a Coulomb interaction might start being difficult, right? Because that's decays quite slowly. There are results for power law interactions. I don't know them offhand. They're probably weaker. And the other important thing is that the Hamiltonian is bounded. For example, so if you have a boson on a site that has an unbounded Hamiltonian, you also might have to work more in that setting. Yeah, so a finite on-site Hilbert space and bounded in space interactions. That is enough. So, for example, if you've got a solid, well, okay, I guess the sound, yeah, something. Okay, I'm going to say sound involves phonons, which are bosons, but okay. There's like zero sound in a Fermi liquid, okay, had better be less than the Lieb-Robinson. Its velocity should certainly be less than the Lieb-Robinson velocity. For any physical or spin waves, right? So if you have some spins, they might have some ferromagnetic spin wave or something. Its velocity had certainly better be less than the Lieb-Robinson velocity. Yeah. But good. Okay, cool. Right. So now what I'm going to do basically is a really simple thing, which is but it turned out to be quite. It's just a Fourier transform this bound basically. Okay. So let me write. So given I'm going to think about the fermionic operator. So that has a retarded Green's function as a function of omega and k, which is defined as follows. So it's minus I. You sum over the lattice. You integrate over time from 0 to infinity, right? Because it's the retarded Green's function. E to the I omega t minus I k dot x alpha. And then you have this expectation value on inside the operator at t, the operator at 0, expectation value. Okay, that's the retarded Green, right? It's the Fourier transform of the correlation function over the whole lattice, but at positive times. Yeah. Good. So because this is a lattice model, you can actually show this thing exists, a real omega and k. Okay, this Fourier transform it exists, but it's more. Now we're going to ask, what about complex omega and k? And we ask, over what range of complex omega and k does this transform exist? And you might worry because here you get terms that can exponentially grow or exponentially decay. If omega has an imaginary part, it's not totally oscillatory, right? So you get some exponentially growing or decaying terms from here, and these have to fight against the exponential decay in the Green's function. Right? So I've shown the Lieb-Robinson bound implies that this thing decays exponentially outside of a certain light cone, and then we have to combine that with how these might behave, and that will give us some bound of convergence. Okay, it's a very simple calculation. So let's let omega 2 be the imaginary part of omega, and I'm going to let q be the imaginary part of k. But it's complex, so there's a real and imaginary part for both. Then we ask, when does this converge? So this is a standard thing in relativistic physics, okay? But our bound is a little bit different from the relativistic bound. You'd have a zero outside the light cone, right? In essence, look, so okay, where does analyticity of the S matrix comes from? That when you take the Fourier transform of a step, you get something with a lot of analyticity, right? But if you take the Fourier transform of something that decays exponentially, you also get a lot of analyticity. That's the idea. So, for example, we could take maybe I can even do it here. We can take the norm of this this object. We lose the I. We get a less or equals than, because I take the norm inside the sum and inside, maybe I should do it a new line. Actually, so the norm of this guy isn't less than the sum over the sides. The integral here, in this bit, you only get the exponentials, so it's e to the minus omega 2t plus q x alpha, and this comes from using q dot x is less than qx. Okay, that I've used that there. And then here we have the norm, the expectation value of this, which is less than the norm ctx. This, we know how that behaves, we know how this decays, and we just ask for what omega and q does it converge. If it converges, it's also analytic, because when you differentiate with respect to omega or q, you just bring down factors of t or x, but those are power law, and they're always defeated by the exponentials, so you can take as many derivatives as you want. So I won't go through it, but it's a simple, so you consider convergence along rays, right, of the form where t is some slope times x over a, right? You just go, you have like a t and an x, and you consider different rays, and you ask whether this integral converges along these rays. Okay, so what you find is the integrals converge on the following domain, and therefore the Green's function is analytic on the following domain. So this is going to be Q, the imaginary part, right? The real part drops out. You can have any real part of any real frequencies and momenta. It's the imaginary part of the frequencies and momenta that matters. This is Q, the imaginary part of the momentum in lattice spacing. And here we're going to have the imaginary part of the frequency in terms of H, in terms of the microscopic energy scale. And so here you get a light cone, where this is velocity v. And then when you hit the lattice scale, so at 1, it bends up and looks like this. Okay, so this is omega 2 equals VQ. And this bit here is omega 2 over H equals e to the AQ. It bends up. So what is that saying? it's saying, so, and here it has to be 100% analytic, okay? Like there cannot be any non. So when you're below the lattice scale, right? So here, this is as good as a relativistic light cone. So when you do this thing in a relativistic theory, you get a sharp, you get a domain of what the sharp light cone buys you is a domain of analyticity. So in particular, at low energies where you might have some quantum field theory emerging, um, you have a light cone that's in frequency space as strong as a relativistic one, and then at higher energy, if you probe theory at the lattice scales, then it's weaker. There's less. There's still some analyticity, but it's not. The light cone doesn't continue. It gives you a smaller region of space that's analytic, right? Now we're on a lattice, so the imaginary part of K is in this some Brillouin zone, right? So the real part of K is in like 0 to pi over A, right? But the imaginary part of K is not constrained. There's no lattice in the imaginary direction. Okay, so I think that's really the first and maybe the most interesting to me punchline. So Lieb-Robinson causality implies a low energy light cone in this sense in omega 2 and Q that is as powerful as a relativistic one in this analyticity sense. Of course, we don't have Lorentz invariance, right? It's not the theory does not have to be Lorentz invariance, but causally it has to have this as a strong light cone. Yeah. So to recap with something that you might know, for example, when this Q is 0, then you're sitting here, and then it has to be analytic for all omega, and this is the analyticity in the upper half plane that you might be familiar, right? Retarded Green's functions are analytic in the upper half plane, but this is a stronger version of that now allows you. It says if you have some imaginary momentum, the domain of analyticity gets smaller. Yeah, that's the new thing that we have compared to Cramer's chronic or kind of results. Yeah. So let me give you two applications, two examples of that. So yeah. So this is the sort of technical result that's relatively low tech, but I think it's fun. But I'm going to give you two applications, but yeah, any questions before? Yeah. Okay, cool. So let's do one. So one is going to be to non-Fermi liquids, which I'll tell you what they are in a second, and the second one is going to be to diffusion, but there could be many. So let's do application to non-Fermi liquids. The point being that non-Fermi liquids are an interesting class of effective field theories that you get in metals that are often strongly coupled, hard to understand. So if you have constraints on them, then you learn something. Yeah. So clearly, right. So okay. So what happens in a Fermi liquid? So if we want to be at low energy. You can ask where are the low energy excitations, right? So you have a boson in a relativistic theory. There's some linear dispersion, right? Omega goes like K. And so all of the low energy excitations are also at low K, right? But when you have fermions at a finite density, then there's some Fermi surface of filled states in K space. And low energy excitations are particle hole excitations, where you take an electron close to the Fermi surface and it just hops out, right? It's called a particle hole excitation. And these are the low energy modes of a metal, okay, of a Fermi liquid. And so the low energy modes live on the Fermi surface. So there's actually many more low energy modes in a metal than there is in a relativistic theory. Yeah. So low energy modes live on the Fermi surface. And so if you zoom in, if you look close to the Fermi surface, they have a linear dispersion. Omega is Kf minus K times some Fermi velocity. So I'm going to write that as Vf K perp, right? So K perp is the distance from the Fermi surface. Right? So it's a linear dispersion, but not about the origin, about the Fermi surface. Okay, so if you have free fermions, what does the Green's function of the fermion looks like? It will look like 1. So let's do free fermions. First, it will just look like something like omega minus VF K-pub, right? Plus some I epsilons to put things in the right place. Okay, that's the retarded Green's function of a free fermion. Now, when you have interactions, you start getting things start decaying, right? And so you get some imaginary parts in this Green's function. And so what interactions do? They can renormalize the residue, so you get some A on the top. You still have your linear dispersion, but now there's going to be some imaginary parts, yeah. And so, for example, in a Fermi liquid, okay, I should try to, okay, in what I write, I'm not going to be super careful. I will in a second, but there are I's and minus signs that you have to put in the right place. But in a Fermi liquid, so that's what Landau discussed many decades ago, you have an omega squared here, okay, plus higher order terms. So this is the leading analytic correction that you get from some 4 fermion interaction, okay? And omega squared is less than omega, and so this will broaden, right? So this if you sort of do a particle physics experiment, right, you're going to get some resonance at the dispersion, and its width is less than its energy, right? Because the interaction is the imaginary part is omega squared, which is much less than omega at small omega, and so it's a long-lived excitation. Okay. So a non-Fermi liquid is when this term is more complicated and often stronger than omega squared. Okay. So a non-Fermi liquid. So there's a class of non-Fermi liquids which are defined a priori just experimentally. Okay, it's something you can go and measure. There's something called angle resolved photoemission spectroscopy. You shine a light at your sample, it kicks out an electron, and you change the energy and the momentum of the light that's coming in, and you see how many electrons you kick out. And from that, you can get some information about the Green's function of the electrons. Okay. And so what you measure, and then you can try to write down effective field theories that capture that, but it turns out to be quite difficult, okay, because they tend to be strongly coupled. So, but one class of non-Fermi liquids is you have this A. Now, let me write this in terms of Z and K, where Z is omega, but I'm already thinking that I might want to let the frequency be complex. Okay, so I just base this Z. So there's Z minus VF K perp minus, now I'll get the I lambda minus I Z alpha lambda to the alpha. Okay, let me explain what I'm doing here. So this is just some parameterization of the IR, right? So the logic is you know the UV, you measure the IR, and you say, I haven't derived this IR from the UV, that's too difficult. Okay, but I just measure the IR, and I say, what constraints are there on the parameters that appear in this effective, given this description, okay? So what are the parameters? So there's this is sort of the wave function renormalization, if you like. Okay, there's some amplitude as a pole. There's a velocity that can also, it's a renormalized velocity. It's not in the UV thing in general. So this is the cutoff. I put in some cutoff. So this only holds. This is for Z less than lambda. Okay, lambda is a cutoff scale. So this particular form it doesn't hold all the way to the UV, right? It's an effective description. And I put these powers here, and there's this power. And I put these factors of lambda here to make little lambda a dimensionless coupling. Okay. If you like, it's the coupling at the cutoff scale, right? That's how it's defined. And these various factors of I's, well, you can verify that they have to go there just by Cramer's conic. So it basically there's a branch. You want the pole to be in the lower half plane, and that fixes that. Okay. So what I'm going to do now is, so this is a plausible. So we call this a Hertz liquid. Okay, this is motivated by something called Hertz-Millis theory, but let's call this a Hertz liquid. Okay. It's just a phenomenological parameterization of possibilities. Now, what you can do is plug this into this analyticity constraint, right? And so this thing has a pole, and this pole in the omega plane. Okay, so good. I'm going to set z to be I omega 2, and I'm going to set k perp to be iq. And this thing has a pole. This pole must be outside the analytic region, at least at frequencies for which the effective field theory is valid, at low frequencies. And so let's see, where is this pole? So it's quite a nice thing. So let's do that. We're going to have I omega 2. That's this minus VF IQ minus I lambda minus I times I omega 2 to the alpha, lambda to the alpha minus 1 equals 0. That's where the pole is. So these i's cancel, and you can take the other i's out. And so omega 2 minus VFQ minus lambda omega 2 alpha lambda alpha equals 0. Right? That's where the pole is on the omega 2q plane. And let's zoom in at low frequencies. So the light cone is just something like this. Okay. So a nice thing about this causality, this analyticity from causality, is that it's obvious that this is a velocity, this is the dispersion, right? And that involves things moving around. But this term isn't a dispersion, it's a dissipation, right? It's like a damping. And it's not totally obvious a priori how to connect damping to causality, right? Because nothing's necessarily moving at that speed. But this analytic treatment just captures them both at the same time, right? All right, so what does this look like? So let's go to small. One can in principle solve this for some given alpha. And at small, let's say that alpha is bigger than 1 to begin with, okay? So then at low frequencies, these two terms are more important, and this thing follows a line like that. Like this. And so clearly, you'd better have VF less than V. Okay, that's not going to surprise anybody, right? This Fermi velocity should be less than the Lieb-Robinson velocity. But then, as you start, because of this term, this thing starts moving up. And the question is, does it go into here before you reach the cutoff lambda in your effective field theory? Okay. And it turns out that the condition for this to happen, so if alpha is less than 1, that's when, what happens then? That's when it's a really strong non-Fermi liquid. It's like a super broad thing. But because of that, everything is actually very slow. Because, for example, suppose alpha was 1/2, just for example. Okay, then at low omega, this term is bigger than that term. And omega would go like k squared in this case, right? Which is sublinear. So it's moving nothing's moving very quickly. And so actually, in this case, it's always fine because it turns out it's really more like that. It's a very slow thing. Okay, it's not believe me, that it is true. I mean, it does eventually intersect, but it intersects above the cutoff. And then if alpha is bigger than 1, then you find that lambda, get the absolute value of lambda, has to be less than 1 minus VF over V. Okay, and it's not a hard thing to do. You just evaluate this pole at the cutoff, you see how far it got, and if it's inside the light cone, that's bad. All right. Now, typically, I think we might expect VF to be much less than V, because V is a really microscopic velocity. Okay, I mean, it's not essential. I'm just to illustrate, but this often happens. And so in that case, it's just a statement that this dimensionless coupling has to be less than 1. Okay, and this is a new bound on a non-Fermi liquid. Okay, and I think it's very much in the spirit. I don't know how many of you are I'm certainly not a bootstrap type person, but this is the kind of thing that happens. You put in an irrelevant operator, right? Because the fact that alpha is bigger than 1, meaning it's not messing up the IR totally. It has it's a non-analyticity, right? it's not omega squared. It's stronger than omega squared, but it's not completely destroying the IR. So it's an irrelevant operator, and if the relevant coupling is too big, it messes up something in the UV, right? That's the thing. So this is a, but this is a totally, I mean, this is not a Lorentz invariant theory, right? But nonetheless, there's a light cone and it constrains the magnitude of the coupling. Okay, and now what would have been really, what we did not manage to do that I would have made me very happy is the most important, experimentally, the most important case of these is actually alpha equals 1. And that's something called a marginal Fermi liquid. And you get a log in that case, right? So that's the Green's function is schematically omega minus VF K perp minus I. Okay, again, I'm not worrying about minus signs and stuff. It's essentially it's something like this, and with the lambda here, and this is actually widely observed in high temperature superconductors and systems like that. And it would have been very, very nice to bound this coupling, but okay, our argument doesn't hold in that case. It's too strong. Okay, but I just mention it in case any of you get inspired. Probably that might be possible. Okay, so let me give you another application is to diffusion. So in fact, causality bounds on diffusion have been discussed for a long time. Maybe some of you might even know. So in the quark gluon plasma, it's relativistic, also has diffusion in it, but diffusion is not causal. Okay, and so if you want to have a Lorentz, a causal code, causal in the Lorentz sense, you can't just put diffusion into it. And so there's this whole Israel, Muller, Stewart, etc. theories where people try to salvage causality and diffusion. Okay, and so what we can do is sort of apply some. So actually, a few years back, I suggested we could apply a similar logic in lattice systems, but now it's really rigorous with no squiggles. Okay, these are sharp inequalities. So what is diffusion? So diffusion is omega equals minus I. So now this is not the Green's function for the C dagger, but for the charge density, right? So the charge density is C dagger C, right, on the lattice site, and this charge density diffuses at longest scale, so or energy density, whatever you want, energy density, charge density in these lattice models, because you don't have translation invariance, right? So there's not a sound mode, okay, a priori. I mean, okay, it's a long story, but okay, there's often diffusive modes, charge diffusers, for example. So, okay, and so let's look at that. And so let's take omega equal I omega 2, K equals to IQ, right? So this is the pole, sorry. So the density Green's function as a function omega and K has a diffusive pole with this dispersion, okay? Again, nothing is dispersing, it's just decaying because there's an I here. So when you look at this, at these complex frequencies, you're going to get I omega 2 minus I d IQ squared. So I squared is plus, and these cancel. And so omega 2 is d q squared. So let's draw that. It's q omega 2. Here's our light cone, and this looks like that. Okay. And so the fact that it goes into the light cone here is the fact that diffusion is a causal, and that it's a simple thing, right? If when Q is small, this is a sublinear dispersion, but when Q is big, it goes faster than linear, right? So okay, so what do you have to say? Well, then it must be that this intersection point has to be above the cutoff for your diffusive theory, right? Because diffusion is not a microscopic thing. Well, it cannot be. So this shows you that you cannot have a lattice model that is purely diffusive, right? There has to be some cutoff. And in the context of diffusion, which is about conserved quantities, this is a natural definition of the local thermalization time, right? So, for example, Fourier invented diffusion to describe heat diffusion, right? But for temperature to diffuse, you have to have a temperature in the first place. And to have a temperature in the first place, you have to have local thermal equilibrium, right? So so the cutoff for diffusion in energy is naturally the local thermalization. In fact, you could really take it as a definition, one definition of the local thermalization type. And so what you get, it's easy to find this intersection, you get that the diffusivity has to be less than the Lieb-Robinson velocity squared times the local thermalization time. Okay. That's just a bound, an upper bound on diffusion, or if you like, a lower bound on the thermalization time. So actually, I wrote this equation down like 6 or 7 years ago, but we had a squiggle. There was some kind of squiggle here, and now it's just absolutely, these are just well-defined things, and it's really a sharp light cone. The fuzziness of the Lieb-Robinson light cone does not create a fuzziness on this bound. Cool. Good. Well, actually, we do have a bit of time, so I can. This is the second paper. Okay, so the one I just told you is about causality. The first paper, are there any questions about causality before? Because otherwise, it's going to be something totally different coming up.
Maybe I have a
Cool. Yeah, Julian. Yeah.
Can you repeat the marginal Fermi liquid, the alpha equal 1 case, why the log prevents
Yeah. Okay. So why it's a log, you mean, or why it doesn't hold, or how with the log?
Why it doesn't hold, why it prevents?
Yeah. So it's on the wrong side. So right, it falls under the case, right? Again, a bit schematically. So this at low omega, this term is more important than this term, right? So it's more like alpha less than 1 than alpha bigger than 1. Okay, even though it's sort of in between them, it's marginally relevant, if you like, not marginally irrelevant. And so what happens is, but the limit is a bit subtle. The alpha, so there's an alpha goes to 1 limit, which I can talk about if you like, but if you like, it's sublinear, and yeah, it just doesn't go up, and the coupling is, but it's somehow intuitively, it's somehow that at the very lowest energies, there's not even anything dispersing linearly. It's only a little bit sublinear, but it's still sublinear, and you can just check in the formulae that it doesn't work. And it might seem a bit confusing that this is sort of a discontinuous limit in terms of this bound, right? Because alpha doesn't appear in this bound, right? But it sort of depends a bit what you keep constant as you take the limit. And so for example, so if you have omega to the alpha, right, you write that as omega e to the alpha minus 1 log omega, right? And then you write that and you expand this, right? But to really, and then this, what you do with this term is you absorb it into the bare term, which renormalizes a bunch of things. So the limit is a bit, and then you have to have, so lambda should have some 1 over alpha minus 1 in it. Okay, we do it in the paper a bit carefully, but sort of this alpha goes to 1 limit is not that smooth, basically. Yeah, depending what is smooth, but not in the variables that I've written. So these is not natural to keep lambda and VF fixed as you take alpha to 1. Okay, and if you write it in the right way, the bound automatically gets satisfied as alpha goes to 1. But okay, it's a short argument, but I won't do it. But the more physical one is that whenever alpha is less than 1, nothing is dispersing linearly in the IR. Everything's sublinear, and so you're kind of a long way away from a light cone, and then you can't catch it within the effective field theory. It turns out. Okay, I don't know. That's
so is the bounds that you write, you expect them to not hold at all in this case, or is just
no, they're always satisfied. Sorry, the statement.
They're ineffective at constraining.
Exactly. Yes, that's what I mean. Yeah.
Okay.
There may be more powerful ones that are, but this one is not. Yeah. Yeah. Enrico, did you have a question too? Okay. Cool.
Okay, can I ask also one question?
Yeah.
So until now, essentially, we are not doing nothing with the analytic structure of the. I mean, you're choosing a model and this model have some analytic structure depending on the coupling, right? But is it known from general principle what's the analytic structure outside with this strange light cone that you are drawing? So are there branch cuts, only poles, poles and branch cut where are located?
I think not much is known at, so let's, okay, I think this wasn't the question you asked, but a related close, let me make a related point I think is quite interesting. So in a relativistic theory, there are singularities on the light cone, for example. And so you could,
Right.
one thing you could ask that I do not know the answer to is whether this analyticity light cone is sharp in the sense of there being some non-analyticity on this
Precisely
light
there,
cone.
right?
And if there is, it might be quite weak because it's quite a UV thing. This light cone and the overlap with low energy states might be quite small. Like because it could be some very high energy process that actually goes at the Lieb-Robinson velocity. But I think it's quite an interesting question whether there's some like mild non-analyticity along this. That's one thing that's not. No, I think that wasn't quite what you meant, but okay, it's a bit related. Let's see. So wait, so what, the questions were there branch cuts or poles? Was that the what?
Right. What essentially what that, because you mentioned this relation, or at least this analogy with S matrix, but in that case we know essentially the most general analytic structure essentially. Here instead you are only saying that there is a region which is analytic.
No, but I think this general, I think the so certainly this good. There's like these you can do a sort of spectral decomposition. I mean, if anything, things are probably nicer than in continuum quantum field theories, right? So for example, these Green's functions decay at the large omega limit is under quite good control, I think, of these Green's functions, for example. And so like you can often close the contour and the top without having to subtract stuff. And so it's easier to prove sum rules and things like that. So a bunch of things are easier. I don't actually know. So I would have thought that you basically should have almost everything in terms of analyticity that you have for an S matrix and perhaps more, with the exception that the light cone is this different light cone.
Okay.
But I don't know. Yeah, I don't know whether you mean whether you could have something worse than a pole, for example. Is that
right? I mean, you can impose, in principle, you can impose, if you know something else about the structure, you can impose more, right? You can write dispersion relation, you can do more.
Oh no, that stuff works. Yeah, you definitely can. Yeah. So
okay.
we have some stuff in the paper at the end. Actually, the first paper about so you can definitely do like these little bumps, right? Is it this right? And because it certainly is so for example, the easiest case would just be to set k equals 0, and then you definitely, but yeah, you can definitely do dispersion relations, and I think if anything, it's easier because these things at infinity are quite mild. Yeah. In the first paper we have a few comments, but we didn't do it systematically, partly because okay.
Let
me tell you that's right. So let me actually maybe in the last 5 minutes let me tell you what we did in the first paper very very quickly, because it relates exactly to this question, which is that to really do a bootstrap, S matrix things, we would like to know a bit more about the positivity properties, boundedness properties, okay? And that's, for example, so it's trivial to show that the imaginary part of the retarded Green's function at real omega and k definitely has to be positive. Okay, there's some convention about whether it's positive or negative. But in my convention, let's say positive, but this follows directly from the spectral decomposition. Okay, so you can insert a bunch of bases of energy eigenstates. You do a few manipulations. You take the imaginary parts, and you get something that's manifestly positive, sign definite. Let's say. But we would also like an upper bound on this thing, and that this in general doesn't have an upper bound, but in a lattice model, it does. Okay, with the local lattice. And so let me be very quick. So using the spectral decomposition, so this imaginary part on the real axis, and this is what you want for is equal to sum over energy eigenstates. Let's look at a thermal state now, for example. And let's say this is for the charge density, but it could be whatever operator you want. Times some whatever. Okay, I'll define everything in a second. Okay, so imaginary retarded Green's function. There's some Boltzmann factor. You're summing over all energy eigenstates. There's the overlap of the operators with the energy eigenstates. There's a Bose-Einstein factor. There's a delta function that says only at a given frequency, you only get contributions from processes at that end, that things hop around between two energy eigenstates at that frequency. And similarly, you have to conserve momentum up to lattice vectors. Okay, that's okay. This is manifestly positive, all these terms. Okay. Right. So now what we can do is right, the problem with these delta functions. Yeah. So one thing you can do is integrate this over some range of omegas and some range of k within the low energy theory. So take some region that you know you control over, and you integrate this. Then you start picking up delta functions, but some of them are outside of your range that you've integrated over. However, because all the terms are positive, you can just extend the range of integration and it can only go up. And so this has to be less or equal than essentially the integral of this over everything. Okay. So I'm being a bit quick because of the time, but what you end up getting is 1 over, and also this Boltzmann factor is decreasing. Sorry, I'm going too fast. A natural quantity is the retarded Green's function over omega, because it's always odd, this imaginary part. So it's very often you get it. It's very natural for it to divide by omega. You get omega. You get this thing, some Boltzmann factor like that. Okay, this new. Okay, well, 1 over a to the 2d. This is like the volume of a unit, the square of a volume of some cell in space. And then you get again, I know this is a bit quick. This sort of overlap factor. But what is this? So here, I've done this integral over the delta functions, right? That's what I got rid of. The sum over m, you can just do it. It's just a resolution of the identity. So this is just equal now to sum over n. Squared. But this is just equal to the thermal expectation value of n0 squared. Okay, which is a very microscopic, like in quantum field theory, you can't square an operator, or you probably don't want to square a local, like maybe you can, but okay. If on a lattice, like this is not a scary thing, right? You have the charge density. The charge density squared is just some operator bounded by 2 or something. Okay, and so there's the integrated spectral weight, where you could do the integral only over some low energy region where the Green's function is bounded. Right, so upshot is some integral over the retarded Green's function is less than some expectation value in sort of in some UV cell. Okay, and so this good. Okay, so this roughly is a. I wanted to think of this as analogous to this upper bound coming from unitarity. Okay, some extra constraint that you have. Wondering what I can tell you that might be, well, okay, you can apply this to some, so for example, say this is the density Green's function. No, and let me not start giving you details. Basically, this, you can use this to constrain parameters in some EFT. Okay, and in the paper we give an example of diffusion. and we essentially show that. So suppose you have two things, so diffusion plus the relaxation time. So this is like your local thermalization, same tau as before. This defines a length scale. So d times tau square root is some length. It's like the mean free path, except I'm not making reference to any microscopics, right? But this is the natural mean free path. So you think of this as the mean free path. And so we show that if your effective field theory is just diffusion plus this effective field theory plus this relaxation time, then L has to be bigger than the lattice spacing, for example, okay, with some numbers. And that's the kind of pretty reasonable. But again, it's no particular model, right? You just assume some IR behavior. You know that there's a lattice in the UV, and this kind of constraint can constrain the parameters in your lattice model. Sorry, in your effective field theory. But in this paper, we also did talk a bit about dispersion relations, but we didn't find a kind of killer application of them in this context, but it might be possible. Okay, thanks for listening.